when we discuss the propagation of errors, most important thing that you have to remember is that typically from this section only numericals are asked. So we will only be asked to propagate the error correctly in certain kinds of problems. So what those problems would be, let's discuss some of those. So here is an example. Here what the scientist, what he is trying to do is that there is a flask. So he has a flask, and in this flask there is a certain quantity of liquid which is there. There is not one flask, but there are two such flasks, okay, and each of these flasks there is a certain quantity of liquid. We want to measure the mass of the liquid, but of course the liquid cannot really be measured without the flask itself. So what the scientist has done is that he has first measured the mass, the weight of the mass of the flask plus the contents. This is M1, okay, and he has also measured the mass of the flask itself when it was empty. So only if you look at the weight or the mass of the flask, then this is M1. Similarly, this also has been done for the second one. So this is M2, the flask itself, and then capital M2 is the weight of the or the mass of the flask plus the contents. What we need to measure is that we need to measure the mass of only the contents in the two flasks added together. So what would that be? That would of course be the weight or the mass of the contents in the first flask, which is M1 minus M1. If I subtract from the total mass the mass of the flask, then I will get the mass of the contents, plus I will add it to the mass of the contents in the second flask. This is what I want to measure. But I not only want to measure this quantity, the basic quantity, I also want to measure the error in this quantity which I am measuring, the total mass that I am measuring. I also want to measure the error in that. So of course, first let's just compute the value of the quantity itself. This will of course be 540 minus 72 plus, this will of course, second one will be 940 minus 97. Very, very simple, not difficult at all. If you compute this comes out to be 1311 grams. Okay, we will just write G. Okay, so we'll just write G because that is the symbol, that's the standard symbol. Now what about the errors? See the error, okay, so we will say M. And what about delta M? That is the absolute error. No matter whether the quantity is being added or subtracted, the absolute errors always get added. That is what we have studied. So that will equal to delta M1 plus delta M1 plus delta M2 plus delta M2. Okay, this is what it would be, right? We will always add the absolute errors. So delta M1 is what? 10 plus delta M2 is 1 plus 20 plus again 1, and if you compute this comes out to be 32 grams. Now what we have studied is that we would, if you look at the previous classes, we would always express the error in one significant figure only. We will never express it in two significant figures. And what is the significant figures? We know that the first significant figure we can find out by starting from the left hand side and looking at the number. The first non-zero number that I have, which is 3 in this case, I will keep that. Others I will make 0. So this error we will express it only to one significant figure. So this becomes 30 gram. Now in the case of our main quantity, since our significant figure appears in the tens location, right? In the case of error, our significant figure is unit tens location. So I I can only say about this tens location. I cannot say anything about the units location. My error is already there in the tens location. In this location, I already have error. So this units location, if I write 1, 2, 3, 10, 15, it does not matter what I write here in the units location. I do not know the value of this unit location at all, because even this digit, this tens location has error in it. I know that it has an error in it. So what I'll do is that I will make this, round this completely to the tens digit. So this will, if I round it off correctly, this comes out to be 10 gram. Okay, and I have rounded both the error as well as the main quantity that I have calculated to the tens location. In both the cases I have done that. And if you write now the final answer correctly rounded off, then the final answer becomes 1310 plus minus 30 gram. Okay, so if you have not done your rounding correctly, if you have not done correctly expressed your error to just a single significant figure, then this answer in all other cases is wrong. This is the correct answer. This is the correct form of the answer that we should always sort of write in. Okay, and if you are not clear about why there are several examples, other examples we have discussed, so look up those videos on this channel. Now here is another problem. In this case, what we have discussed previously in the class is that sometimes we can use, if for example, I cannot accurately measure the thickness of one paper. What I'll do is that I'll create a bundle of these papers, I'll measure its thickness, and from that, if all the pages, if all the sheets have the same thickness, I can, from that measurement of the bundle, I can now derive the measurement of thickness of a single sheet. So that is what we have done here. We have taken 100 sheets of paper and its thickness I have found out to be this much, okay, with some error of course, and from here I want to derive the error in my measure, I want to derive the thickness of one sheet correctly expressed with error. Okay, so obviously the thickness of one sheet, we will write it as small t, that can be found out very easily, that is 1.3 divided by 100 inches. So this comes out to be 0.013 inch. Okay, what about the error? We have already studied in the previous class that the error in the case of the measurement, okay, of the entire bundle would be divided by 100 also, because our main quantity is divided by 100. So our error 0.1 inch would also be divided by 100 when we calculate the thickness of one sheet. Okay, and this happens because t is equal to 100 t, therefore my delta t will also be equal to 100 delta t, or delta small t will be equal to delta t by 100, which is equal to 0.1 divided by 100, and if you compute this comes out to be 0.001 inch. Okay, notice that this is the case with absolute errors. Okay, this division would only hold for absolute error. This formula only holds for absolute errors. In case of relative error, the relative error of t and t in both these cases, okay, which is the delta t by t, that is the relative error, is actually equal to delta t by t. Okay, but here we are interested in the absolute error. So in the case of absolute error, we can write delta t as 0.01 inch, and of course my final answer, which is delta t plus this delta is not there, t plus minus delta t, I will write it as 0.013 plus minus 0.001, and there is an inch here. Everything is already expressed to correct number of significant figures, so I don't really have to worry about anything there. So this is my final answer. Now here is another example. Here what the person is trying to do is that what they are doing is that they are taking an object, for example remote. In this case I will not really throw it down, but what they are trying to do is very, very simple. What they have done is that they have raised this object, a stone in this example, to a certain height, and they have thrown this stone from that height, and this height is h, and they have a stopwatch in their hands, perhaps from their smartphone nowadays, okay, and using that stopwatch they have measured the time t taken for this stone to fall to the ground. That is what they have measured. And with this measurement of h and t, now we are trying to find out the acceleration due to gravity, or g. We already know that there is a formula for giving us the distance covered in terms of the acceleration. So that is of course half at square. In this case acceleration is g, so this is half gt square. So of course g will come out to be 2h by t square. Okay, so we have to find out the error in the computation of g. See, the value of g has already been computed. The person has already computed the value of g to be 36.1 feet per second square, and now we want to find out the error in g. That is, we want to find out the value of delta g. So let's just again try to do that. Delta g would be equal to the error in h, which is delta h, plus, because t is raised to power of 2, okay, that is why we will multiply the error in t to be delta t. But there is a problem with the formula that I have written, and the problem is that these things would not be absolute errors, but these things have to be relative errors. So this is delta g by g, this is delta h by h, and this is delta t by t. Because in the case of multiplications, divisions and powers, we always have to use the relative errors of the quantities, and finally in the final answer also we get the relative error in our computed quantity. So that is the very, very important thing. Another thing to note here is that this 2 is coming because of this power 2. Okay, it is not coming because of this 2 right here. Okay, the formula, there is a constant there, but that is not factoring here. Because t is raised to power of 2, that is why we are multiplying the relative error of t by 2. That is another thing to note here. Those are the two things that we have to really understand. Now from here things become very, very simple. What is the error in h? The error in h, or delta h by h, is actually equal to, very, very simple, it is 0.3 divided by 46.2, and if you compute this, this comes out to be 0.007. What about the error in t? If you want to compute this, the relative error in t is delta t by t. This comes out to be 0.1 divided by 1.6, and this comes out to be, if you find out its value, this comes out to be 0.63. Okay, very, very simple. So far we have not done anything complicated. Now I plug this 0.163, I plug this in 0.007 in my formula right here. Okay, so here I will just plug it in, and what is the final value of delta g that I'll get? Delta g by g, or relative error in g, I'll get, that will be equal to 0.007 plus 2 into 0.063, and if you compute this, this comes out to be 0.133. Of course this is relative error, this is delta g by g, so absolute error will be delta g is equal to 0.133 multiplied by g. G we have already computed, 36.1, so this becomes 36.1, and if you find this out, this will come out to be 4.8. And of course, because we have multiplied, see, the relative errors is always dimensionless, but as soon as I multiply it with g, I get dimension here. So this is feet per second square. Okay, as soon as I multiply it with 36.1, my final absolute error delta g, it will have some units, and I have to always keep those units with me. In fact, I should write those here as well. So this is also feet per second square. Now of course we have already seen that our errors, when we are expressing absolute errors, we should not keep any more significant figures than 1. The only significant figure we should keep is one significant figure here. So we start from left, we only take the first significant figure and we round it to that. So we round it to units place, feet per second square. Since we have rounded our error to the units place, I will round our final answer to the units place as well, because this 0.1 really has no meaning anything after the units place, I really don't know its value. So that really has no meaning. Okay. So I will just remove that. I will just round that 36.1 to 36. Okay, I'll round it to units place, and I'll express my final answer as, so I'll write my final answer G plus minus delta G, and that comes out to be 36 plus minus 5. And of course, units, we will never forget to write those, feet per second square. Very, very simple. If you approach this problem systematically, it can be solved in the same page in which you have written your question. Okay, so thank you very much. Practice these problems yourself. Always when we are solving problems, take a pen and paper and solve it with me. I'm sure solving problems, the only way to excel at that is to solve many problems yourself. Okay, thank you very much.